Hello and welcome to the Self-Driving Car Nanodegree program. My name is Arvind and I will be your instructor throughout the term 1 of this Nanodegree. First of all, congratulations everyone for making it here. You have made one of the best decisions in your learning career. So in the autonomous space right now, we have two approaches. One is the robotics-based approach and another is a deep learning-based approach. So, a robotics-based approach includes fusion of various sensors to take decisions and help in driving the car autonomously. Another approach that is now becoming very famous is the deep learning approach. So, deep neural networks can learn to drive a car by mimicking the human behavior. So, the term 1 focuses more on the deep learning side and term 2 focuses more on the sensors and the robotics side. Before we start anything, I just want to give you a brief introduction of what we will be doing throughout the term 1. So I will be showing you certain projects and screenshots of what comes next. So we'll start with basic OpenCV and we'll try to find lane lines of the road. This was one of my favorite projects because when I started I actually was amazed at what OpenCV can do for you. In the second project, we will talk about the current buzz in the tech industry at the moment, that is neural networks, and we'll see how to teach a neural network to classify traffic signs in TensorFlow and Keras. In third project, we will use deep learning to predict the steering angles of a car in a simulated environment. This is one of my favorite projects because it reminds me of the video games that I used to play and I hope that you will like it too. In the fourth project, we will turn back again to OpenCV and we'll see the advanced color spaces and techniques for finding lane lines on the curved roads and a more robust pipeline to find the lane lines. And in the fifth and the final project, we will create the most interesting project in term 1, that is the object detection and tracking project. In the final project, you will be using classical machine learning and sliding window approach to develop a detection and tracking pipeline. So this was all about the 5 projects we are going to do in term 1. So I know you are getting excited with the content and the projects that I just show you now, and you are all ready to get started, is it? Yes, so let's get started. So in the week 1, the project that is finding lane lines on road is just a basic project and it should get completed by within the first week when you start attempting this project, while the rest of the projects might take up to a month for you to complete. In case you are stuck anywhere, you can ask for the support from mentors or you can search your questions in the forums. So having said that, let's start. So we'll start with computer vision. So what exactly is computer vision? So computer vision is a field of study which gives eyes to the robots or self-driving cars. Just as a human sees and perceives the environment around with his eyes, the robots or the self-driving cars perceive the environment through cameras. So in the first module, we will take a series of images and you will detect the lane lines on the images. But let me ask you a question. What do you think is the most important feature when you drive on a highway and you are observing the lane lines? Yeah, you got it right. The first feature that is very important is the color. But color may not be the only feature that could be useful in the identification of the lane lines. Other features like shape, orientation, and position in the image can also help you in identification of the lane lines. So you'll think about that most of the lane lines are actually white in color. So what if I extract the white color from the image? So in order to do that, you have to know the color spacing code of the white. So what according to you is the color code of white in RGB color space? Yes, you got that right. Fantastic. It's 255, 255, 255. So the next thing you do is you take a bunch of thresholds and apply those thresholds to different channels of the image. As you know, an RGB image is a 3-channel image. So you take 3 different thresholds or maybe a common threshold and apply individually to all the 3 color channels. So basically pixels have values from 0 to 255. So if you set a threshold of 40, then you are saying that keep all pixels that are less than 40 and discard everything that is greater than 40. So in this way you are able to retain certain color space that you actually want. So the values of this threshold, that is red, green and blue, you can find it using hit and trial and what exactly suits the best. Another point to ponder is that you do not want to find the lane lines that are actually far away from your car. Right? Suppose you are driving in lane number 1. So you only care about the lane lines of lane number 1, right? So you don't need the lane lines of the lane right to you or maybe left to you. You just need the lane lines in the lane in which you are driving at the moment. So how can you achieve that? Make a wild guess. Well, that's pretty close. Your answer is pretty close. Maybe, yes, that's fantastic. You can actually mask a region of interest. And you can say that my region of interest lies only in this area. Now, your camera is permanently mounted to one space in the car, right? Your camera won't be moved here and there while you're driving the car. So, if it is in a fixed position, you can actually mask a region of interest and find only the lane lines in that particular region. So, what exactly you do is, you take a region of interest. Now, this region of interest is also by hit and trial based on the position where your camera is kept, and then you can apply the color masking as we discussed just 5 minutes ago. So, region plus color will give you the lane lines that you care about. So, I hope till now everything is crystal clear, right? Okay, so I have a question for you. So what happens exactly if you follow this approach? If you say that I will always be finding the white lines in a particular region of interest, so what according to you could be a problem? Yes, that's a valid problem. So one of the students says that some of the lane lines that we care about might not be clearly visible or maybe light in color. Yeah, so another student says a very good point. He says that the lane lines might be of yellow color. So it's not always that the lane lines are of white color. So to just give you a starting, that was one of the examples. So the lane lines might be even of red color or might be even yellow. So yellow is quite common, maybe red is not. So what in that case can you do? There is one answer, that you need to make your pipeline more robust. I mean, you need to use more sophisticated and advanced techniques of computer vision. If this was that easy, then yeah, there wouldn't have been this course either. So let's start with one of the techniques in computer vision, that is Kenny edge detection. So with Kenny edge detection, the goal is to find the boundaries of an object in the image. Irrespective of what object in the image is, we just need to find the boundary of that object. So the object could be a car, a person, an aeroplane, a road, a line, or maybe anything else. Our goal is just to find the edges or the boundaries of an object. So there is a particular algorithm on how to do that. So the first step is convert to grayscale. So you take a 3-channel image and convert it to 1-channel image, that is grayscale image. And the next step is to compute a gradient. And that's it. So you get the boundaries of an object just by these two things. So it might be possible that if there are different objects in an image, some may be more illuminated and some may be less illuminated. So the brightness of the object or the boundary corresponds to the strength of the gradient at that point. Now you'll think that what exactly is a gradient? we haven't talked about the gradient anywhere. So consider your image as a function of x and y. So if you have a function f and you have two parameters x and y, so f of xy is equal to pixel value. So a gradient is nothing but a derivative of the function with respect to x and y. That is that how exactly are the pixel values changing in the x direction and how exactly are the pixel values changing in the y direction. After you grayscale and apply gradients, you will get thick edges, and we will use scanning edge detection to actually make those thick edges thinner to just get one line that we care about. So guys, that's it for the demo part. I'm now switching off, so you can let me know what you think about that.